chloramphenicol. This is the structure of chloramphenicol. As we see here, we have 3 carbons, 1, 2 and 3. We have here 2 chiral centers, number 1 and number 2. So we have 4 isomers. Only the D3 isomer is active, but not the L3. D and L3 erythro are inactive. Because we have 2 chiral centers, we have 4 isomers, only the D3 is active and the rest 3 are inactive. How can we name nomenclature to chloramphenicol? Here we will say D3 first because it is the active isomer. In the 2 position we have 2 dichloroacetamido, and in the 1 position we have 4 nitrophenyl. All these are propane, but in the 1 and 3 position we have hydroxyl group, so we say 1,3-diol. Chloramphenicol is obtained by fermentation of Streptomyces venezuela, and its chemical structure was established very quickly, so it is now produced by total synthetic route. Chloramphenicol is a broad spectrum, so it is active against gram-positive and gram-negative. It is the drug of choice for salmonella infection, therefore typhoid fever. And because it can penetrate the CNS, so it can be an alternative therapy for meningitis. And it is also used for the treatment of rectisial infections. Chloramphenicol is considered to be a bacteriostatic, and it causes inhibition to a bacterial protein biosynthesis by binding to the 50S ribosomal subunit. The side effects of chloramphenicol are: they can cause bone marrow depression, so they can cause fatal blood dyscrasia as aplastic anemia, hypoplastic anemia, thrombocytopenia, and granulocytopenia. Another side effect of chloramphenicol is gray baby syndrome. It can cause death to the newborn infants. Why? Because these infants have undeveloped glucuronide and undeveloped renal function. So if you give them chloramphenicol, this will cause accumulation of the drug, poor feeding, decrease in their breath, CVS collapse, and then death. So it is not recommended for the first two weeks of life, because the infant or the newborn babies have no glucuronide and renal function is undeveloped. Another side effect of chloramphenicol, it causes inhibition to some hepatic oxidases. So in this case it will block the metabolism of certain drugs like warfarin, tolbutamide, phenytoin. So these drugs will increase in their concentration. To solve this problem, we these drugs are not recommended with chloramphenicol. What is the metabolism of chloramphenicol? Here, carbon 3 can undergo phase 2 metabolism, forming 3O-glucuronides, which is the major metabolism. Also, we have minor metabolism, as you see the nitro group here can undergo reduction, and also we have amide, so it can go hydrolysis of the amide, and we have 2-chlorine, it can undergo dehalogenation. So the major metabolism is 3O-glucuronide, and the minor metabolism can be by reduction of the para-nitro group, or aromatic, or the hydrolysis of the amide, or dehalogenation. Resistance can take place on using chloramphenicol for a long time. Here we have strains of certain bacterial species are resistant to chloramphenicol by production of enzyme known as chloramphenicol acetyl transferase. This enzyme can acetylate the secondary hydroxyl group and to less extent to the primary hydroxyl group and cause inactivation to the chloramphenicol. So, resistance to chloramphenicol due to the presence of enzyme known as chloramphenicol acetyl transferase, which inactivate the chloramphenicol. We can take a short note about the stability of chloramphenicol. It is very stable in the solid form, but can hydrolyze in the form of solution, and this depends upon a pH, the light, and the heat. If there is an acid, it can hydrolyze the amide. If it is alkaline solution, it can undergo hydrolysis to alpha chloro, convert them to alpha-alpha dihydroxy derivatives. So in the solid form it is very stable, but if it is in solution, there are different factors can cause hydrolysis, as a pH, a light, a heat, acidity, and alkaline. What is the structure-activity relationship concerning the chloramphenicol? As you see here, the nitro group is in the para position. If you put it in the ortho or meta, this will decrease the activity. If you replace this nitro group by another group, it will lose the activity, except if it is an acetyl group, as I draw it in the acetyl group. Here example is called cetophenicol, or you replace it by a methyl sulfonyl group, as example cyanophenicol. These are active compounds. So the nitro group must be in the para position, and if we replace it by another group, it will lose the activity, except the acetyl group and a methyl sulfonyl group, it is still active. Concerning the benzene ring, if you replace it by another group, it will lose the activity, except the nitrocenyl derivative, which is isoster to the phenyl group. Here it will be the same, it will be active but less active than chloramphenicol. But it is less active. So the benzene ring must be benzene ring. If you replace it by an isoster to the phenyl group, it will still be active but less in activity. Concerning the two chlorine atom, if you replace them by dibromo group, it is still active. If you replace the two chlorine and the CH attach them to azidoacetamido, which I draw it by the red by CH2N3, example is azidamphenicol, it is still active. Therefore, replacing the chlorine by bromine is still active, and replacing chlorine and the CH by azidoacetamido, it is still active. Is there any prodrugs concerning chloramphenicol? Yes, we have two prodrugs for chloramphenicol. Chloramphenicol palmitate, and the other one is chloramphenicol sodium succinate. Chloramphenicol palmitate, why we prepare it? Because chloramphenicol is having a very bitter taste, so we cannot give it to pediatrics. So we form chloramphenicol palmitate, which is an ester with the hydroxyl group in carbon number 3. It is still insoluble in water, but can be given as oral suspension to pediatric, having no bitter taste. And by taking them orally, it will undergo hydrolysis in vivo, giving the active form. Why we synthesize chloramphenicol sodium succinate? To overcome a poor water solubility, so it is water soluble, so we can take it by injection. Here we undergo esterification by together with the hydroxyl group in position number 3. Chloramphenicol sodium succinate is water soluble and can be taken by injection and undergoes hydrolysis in vivo, forming the active form. We finished chloramphenicol, then we will start the macrolides. Macrolides, they are isolated from Streptomyces species. From the name macro, they are having a large ring, large lactone ring. They are cyclic ester with 12 to 17 atoms with 2 or more sugars. One of this sugar must be an amino sugar. So the macrolides are weakly basic, they can form salts with acid, and they are water insoluble. They are bacteriostatic, and they inhibit the bacterial protein biosynthesis by binding to the 50S ribosomal subunit. And they are having narrow spectrum. Although the word macro, they are narrow spectrum as penicillin G. So we use them as alternatives for patients allergic to penicillins. There are side effects concerning the macrolide, which are they cause GIT problems. In addition, they can cause cholestatic jaundice. Why they cause cholestatic jaundice? because the bile here becomes granular in the bile duct, so it'll decrease the flow, so the bile salt here will be back into the circulation, causing jaundice. Also, from the side effect is ototoxicity. They can cause deafness to the patient if they are used in large doses. In addition, they can increase the level of certain drugs as anticoagulant, anti-diabetic. Why they cause their increase in their concentration? Because they undergo inhibition of the metabolizing microsomal enzymes. From the side effect also of the macrolides are their accumulation in the liver, so they are not given to patients having hepatic dysfunction. Before and say that the hydroxyl group at C6 will make interaction with the C-carbonyl group at position number 9. So the hydroxyl group will form a reaction with the carbonyl group at position number 9. Then the hydroxyl group at position number 12 will form a reaction with the carbonyl at position number 9, forming this ketal formation, and it releases one molecule of water. So erythromycin in addition has very bitter taste and poor oral absorption. So to solve this problem, we use to prepare it in the form of enteric coated and delayed release for the dosage form of erythromycin. Because it has a very bitter taste and poor oral absorption, we prepare it in the form of enteric coated with delayed release for the dosage form of erythromycin. This overcomes the bitter taste but not the poor oral absorption. To overcome this poor oral absorption, we prepare the erythromycin in the form of salts and prodrug, which is erythromycin ethyl succinate. Succinic acid have two carboxylic acid moiety. One of them will react with the amino sugar and the other one will react with ethanol. So in order to give erythromycin to pediatric, we have to prepare a prodrug. Erythromycin ethyl succinate. As we see here from the blue arrows, succinic acid have two carboxylic acid moiety. One will be attached to diazothamine and the other will attach to ethanol. So it is a mixed double ester, insoluble in water and tasteless, so we use it as an oral suspension for pediatrics. In order to give erythromycin intravenous for parenteral use, it is a free base and it is water insoluble. So we prepare erythromycin lactobionate or erythromycin gluciptate. These are erythromycin salts, are freely soluble in water, so you can give them by intravenous. What are the chemisynthetic analogues for erythromycin? We have here clarithromycin. The only difference between clarithromycin and erythromycin that we make esterification. We change here at position number 6 the hydroxyl group by methoxy. We undergo here by semisynthetic esterification. So what is the advantages of this semisynthetic analog? As we said before, that erythromycin can undergo ketal formation, and the first step is the hydroxyl group at position number 6 will make reaction with a carbonyl at position number 9. So here in clarithromycin we do not have the hydroxyl group at position number 6, so there is no ketal formation can be done, which is inactive and causing GIT cramp. In addition, the methyl group here increase in lipophilicity, so it increase the absorption better in the blood levels, and so we decrease the frequent dose. So by this esterification, no ketal formation is formed, and the absorption here is much better, so the dose can be decreased. Another synthetic one is known as azithromycin. Azithromycin, as we see here, is a macrolide, a very big structure. The difference between it and erythromycin that we removed the carbonyl group at C9. In addition, we make here ring expand. It is not 14 atoms as erythromycin, but it is 15 atoms, as we see here, and we introduce N-methyl moiety between the C9 and the C10. The same advantages as before. There is no carbonyl at C9, so there is no ketal formation, which and no GIT cramp. In addition, it is taken once a daily, where the methyl amino group added here increase the lipophilicity and absorption, better blood level, so the frequent dose can be decreased. It has a greater activity against gram-negative than either erythromycin or clarithromycin. It has a great activity against gram-negative than either erythromycin and clarithromycin. Here we finish the macrolide, and we will start the aminoglycoside. They consist of amino sugars linked together glycosidically. Treatment by aminoglycoside must be under close clinical, and this is because of their potential toxicity associated with their use. So by using aminoglycoside, this must be under close clinical and not home because of its potential toxicity. And the prototype of this group is streptomycin. Aminoglycosides, they are specific inhibitors of a bacterial protein by binding to the 30S ribosomal subunit. In addition, they are broad spectrum. They are active against gram-positive and gram-negative, and they are bactericidal, so they can kill the microorganism. General properties of the aminoglycoside. They are bactericidal, having bactericidal effect only against the aerobic bacteria and not the anaerobic bacteria. Why? Because the anaerobic bacteria, because they transport through the cell membrane. The aminoglycoside transportation through the cell membrane is energy requiring process, and this is oxygen dependent. So they are active against the aerobic bacteria and not the anaerobic bacteria, because their transportation through the cell membrane require oxygen, is oxygen dependent. Another general property is they are limited in use. They are used only for severe gram-negative infections. Why? Because of their high toxicity. So they be under close clinical. This toxicity including the ototoxicity and nephrotoxicity. Aminoglycosides are freely water soluble. They have many hydroxylic groups, so they are highly polar. So they are very poorly absorbed from the GIT, so we cannot take them orally. They are used by injection. If you use them orally, there will be for local GIT infection. If you use them orally, this will be for GIT infection. We noticed also that the aminoglycoside with a beta lactam antibiotic, there will be synergism. But if we combine them together in the same solution, they are chemically incompatible. Why? Because there will be N-acylation by beta lactam, so inactivation of both antibiotics will take place. So how to solve this problem and give both them together without inactivation? By giving into different tissue, each preparation one in each arm, so you can give them together but they are in a separate arm. As we said before, there can be resistance by the microorganism to our antibiotic. Resistance here by the production of R factors mediated enzyme that catalyze acetylation, phosphorylation and adenylation of specific functional groups. So in this case they will prevent the binding of the drug to the ribosomal unit, so it will be useless. These enzymes are three types. We have the amino acetyl transferase, cause acetylation to the amino group, and we have the phosphotransferase, which undergoes phosphorylation to the hydroxyl group, and we have also the nucleotidal transferase, which adenylate the hydroxyl group. Pharmacophoric unit. The aminoglycosides are formed of 1,3-diamino-inositol. 1,3-diamino-inositol. What does inositol means? It is cyclohexane hexaol. Cyclohexane, it is known as 6-membered and cycle. hexaol means we have 6 hydroxylic group. As you see the drawing, it is cyclohexane hexaol, and it is a chair form. As you see here, it is not glucose. Why it is not glucose? Because all the ring form of carbon. There is no oxygen in the ring. So inositol, 1,3-diamino inositol or inositol is not a sugar. It is all formed of carbon, cyclohexane. There is no oxygen in the ring. The 1,3-diamino inositol are having 3 types. The first one is known as streptidine. You see the structure here of streptidine. It is inositol, but the 1 and 3 we have guanidine. The 1 and 3 position we have guanidine, and the prototype of this group is streptomycin. يبقى the first type of 1,3-diamino inositol is streptidine, and it contains 1 and 3 guanidine, and the prototype is streptomycin. The third one is spectinamine. As you see here in the spectinamine, it is 1,3-diamino inositol, but the 2 amino group here are substituted by methyl group. So we have in the 1 and 3 methyl amine, and of course the hydroxyl group is present already in position number 2. This is the third type of 1,3-diamino inositol. So the aminoglycoside containing streptidine, we have streptomycin. This is the structure of streptomycin. Here is the streptidine. As you see here, it is 1,2-diamino inositol. In the 1 and 3 position, we have the guanidine. This is a glucose, and this is a glucose. We knew it is glucose because it have oxygen in the ring. The 2 glucose here, in the middle one is L-streptose, and the other one is N-methyl glucose amine. Therefore, in streptomycin, we have the streptidine attached to L-streptose and N-methyl glucose amine. Streptomycin is obtained from Streptomyces griseus. It is used in combination, not by itself, against Mycobacterium tuberculosis. Therefore, it is used to treat the TB, but not used alone. Here is the other one is dihydrostreptomycin. From the name dihydro, therefore we add 2 hydrogen atom. It is semi-synthetic derivative from streptomycin, so it is similar in activity but with delayed deafness, less side effects. We prepare it from the streptomycin by the reduction of the aldehyde position of the L-streptose to alcohol. So dihydrostreptomycin is prepared from the streptomycin by reduction of the aldehyde of the L-streptose to alcohol. The second type of 1,3-diamino inositol is 2-deoxystreptamine. Examples of aminoglycoside having the 2-deoxystreptamine, we have kanamycin. As you see here, the kanamycin. The red arrow showed the 2-deoxystreptamine having no hydroxyl group in position number 2 and having the amino group in position 1 and 3. The blue arrows here showing 2 sugar known by the presence of oxygen atom in the ring. This kanamycin is obtained from Streptomyces kanamyceticus. It is unstable to the R factor. As you see here, the amino group can be acylated and the hydroxyl group can be phosphorylated and adenylation. So we solve this problem by semi-synthetic product. Here is unstable to the R factors. The red arrow showing the amino group can be acylated, the green one can be phosphorylated, and the blue hydroxyl group can be adenylation. So we can solve this problem by semi-synthetic aminoglycoside from kanamycin. Like what? Like amikacin. In case of amikacin, in the one position you have a crate substituted. Acylate the one amino group of the 2-deoxystreptamine ring by LAHBA, which is L-gamma amino alpha hydroxybutyric acid. So amikacin is a semi-synthetic antibiotic from the kanamycin. Here we substitute the amino group in the first of the 2-deoxystreptamine by L-gamma amino alpha hydroxybutyric acid. Here we find that the L-gamma amino alpha hydroxybutyric acid, the L derivative is more active than the D isomer. In this case, it inhibits phosphorylation but not the acetylation at the C6 and adenylation. We found here in the amikacin, it inhibits the phosphorylation but not the acetylation and adenylation. It resists the attack by most bacteria inactivated enzyme. Therefore, it is effective against strains of bacteria that are resistant to other aminoglycosides. Less ototoxic than kanamycin, so higher dosage are required. So this amikacin, it resists the attack. It attacked by most bacterial inactivated enzyme and less ototoxic than kanamycin, so higher dose can be taken. Another example of 2-deoxystreptamine is gentamicin. You see the structure of the gentamicin. We have here the 2-deoxystreptamine. By looking at the glucose, the blue arrow here, the red arrow, no hydroxyl group, so no phosphorylation and no adenylation can take place. However, acetylation here can occur because, as you see in the blue arrow, we have proton attached to the nitrogen, so acetylation can take place in the gentamicin. Gentamicin is having strong activity against Pseudomonas aeruginosa infection, so it is used in this infection. It is heat stable antibiotic it can remain active even after autoclaving, so it is stable over wide pH range. The last one of the types of 1,2-diamino inositol, we have the stactinamine. Example of stactinamine, we have the stactinomycin. As you see here is the stactinamine having the methylamine in the 1 and 3 position, but it differs from all before that it consists of 2 units only and not 3, 1 inositol and 1 sugar. It is obtained from the Streptomyces spectabilis, and it is considered to be the drug of choice in the treatment of gonorrhea.